Okay, so I hope this is one of the easiest mechanisms you have to do to date. Again, we're just going to be replacing a hydrogen from what we had in reaction mechanism 10 with an R group, because rather than starting with a hemiacetal or with an acetal, we're starting with a ketal. So I'm going to go ahead and just go through this mechanism fairly quickly, and then I'm going to highlight two common mistakes that I've often seen with this mechanism to sort of make sure that they're not common mistakes that you guys make when you're working through it. Okay, so again, our ketal here. And just to highlight, when we see something that's either a ketal or an acetal, we're going to see a carbon atom that has two ether connections. And so we're going to then look adjacent to one of the R groups, and we're going to see whether or not it's an additional R group and we're having a ketal, or in reaction mechanism 10, we saw that this was a hydrogen, meaning we started with an acetal. Mechanism is going to be pretty much exactly the same as what we saw. We're going to have protonation of what we want to be our good leaving group. We have departure of this leaving group, which is facilitated by the adjacent lone pair electrons on the heteroatom, the oxygen that's there. And then we're going to have water as our incoming nucleophile here, reacting with this very electrophilic carbon here, generating our protonated hemiketal, which we can subsequently deprotonate to generate our final product. So a couple of things to just kind of highlight here. First, you might ask the question, well, why doesn't this guy come in and nucleophilically attack? And the answer is it absolutely could, but that would take us back in this direction. Remember, when I'm giving you a mechanism, I'm telling you where I want you to go, because I'm dictating kind of the sequence of steps that you need to have happen. So yes, absolutely, this alcohol could come back and react with that electrophilic carbon, but that then just takes us back towards the ketal product rather than moving forward to generate the hemiketal product that the problem is asking about. So hopefully pretty straightforward mechanism, very similar to what we saw in reaction mechanism 10. So on the next couple of slides, I'm just going to highlight some common mistakes that we've seen. So the first common mistake that I often see is people tend to make this kind of mechanism where they have the water coming in as a nucleophile and then a protonated alcohol leave, trying to have that happen in the same step. That is a concerted substitution reaction, sort of like an SN2 reaction. So I'm going to kind of draw what that would look like, keeping in mind what I'm going to draw is not a correct or valid mechanism. So starting here with our protonated leaving group here, again, what students often want to do is to take and have nucleophilic attack and then departure here in what is equivalent of an SN2 mechanism. And again, they then want to generate what equates to a protonated hemiketal intermediate here. But remember, this does not happen, and the reason it doesn't happen is steric hindrance. And just kind of a big theme we've seen with lots of things is that chemistry is driven by energetics and by sterics. And so in this case, the chemistry that students want to draw here is actually inhibited by the steric hindrance around this carbon atom. So, in organic chemistry, you learn, well, if something can't happen because of a steric hindrance via an SN2 mechanism, they want to draw an SN1-like mechanism. So again, highlighting that maybe in organic chemistry you had a tertiary alkyl halide that would be too sterically hindered to undergo an SN2 type mechanism, a concerted substitution mechanism. With alkyl halides, what you'd have is the leaving group just leave and you generate a carbocation. But again, we're not going to see that here for several reasons. Again, even if we did have the leaving group just leave and we were to draw a carbocation, what you're going to see in this mechanism that I'm going to highlight above is that would be a very reactive species. Carbocations are extremely reactive and really would be internally stabilized by the electron pair that's on the adjacent heteroatom, on the adjacent oxygen atom. So again, drawing out this mechanism and again highlighting why this is not something that we'd see. And it's so hard for me to draw these because again, knowing that this is not a correct mechanism. So again, sometimes students having SN1 and SN2 like mechanisms in their brain will be like, okay, sterically hindered carbon atom, I'm just going to have my leaving group leave then, and I'm going to generate a carbocation intermediate. And I'm grateful that I really haven't seen too many carbocation intermediates at this point. But keep in mind that this carbocation intermediate, having an incomplete octet on that carbon atom and a positive charge on that carbon atom, very unstable, we could draw a resonance structure that has electron donation from that adjacent heteroatom to generate an intermediate that is the same intermediate that we had within the correct mechanism. So just highlighting that this is the same intermediate that we saw before. But we don't get to it by this being a two-step reaction. Really, it's a concerted effort by this lone pair of electrons coming down first to facilitate the departure, again, of this leaving group. Again, we don't see a concerted substituted mechanism for the steric hindrance reasons that we talked about on the previous slide, and leaving group departure to generate a carbocation is just not something that's really seen. Even though this is a potential resonance contributor, it's going to be so minor because remember, when we're validating what is kind of a good resonance structure, anything that has an incomplete octet on any atom is not a good resonance structure, and particularly when we have an internal source of electron density from an adjacent heteroatom that can help stabilize that. This is a very minor contributor in terms of the overall sort of resonance hybrid. So this resonance, kind of if we were to draw a resonance hybrid here, this reminds us that that carbon is going to be very electrophilic, but we really are not going to see a carbocation that we draw.